In this video, we're going to talk about scalar and vector projections. Okay, a scalar projection is simply a scalar, a length. And a vector, of course, is an actual vector with new components. So let me explain here some of the notation and then what we're trying to find. This says the projection of B onto A. So essentially, it is, we have two vectors, B and A. B is in blue, A is in, or I'm sorry, B is in red, A is in blue. And the projection is what happens when the vector B is dropped down to make a 90-degree angle onto A. So this is the projection of B onto A. This is the green vector right here. That's called the projection. Okay. Sometimes you'll see people say something about like taking a light and shining it down, and the shadow would be the projection. Okay, so the first thing I would like to do is I'd like to think about what is the length of the green vector. And let's start with some things we could actually calculate. Of course, if we're given vector B, we could calculate the magnitude of B. And if we're given vector A, we could calculate the magnitude of A as well. Now, I think most people will, and so what we're looking for, if I can, is we're looking for the magnitude of the green. Okay, this is what we're trying to find. What is the length of the green vector? Now, I think a lot of people look at this and say, well, you know, a lot of times we can find an angle, we do this, and we could use some trigonometry. We could say that the, you know, for instance, the cosine of theta is equal to the adjacent side, which is the green. I'm going to write magnitude because, of course, that's the length, over the magnitude of B. So what we have here is we're saying the angle, cosine of the angle is length of the adjacent divided by length of the hypotenuse. Of course, the problem is we don't know the angle, right? We haven't come up with a way to find the angle. So let's connect this back to dot product and say, well, I know that an angle is equal to the dot product divided by magnitude. I'm gonna actually erase the dot there just so we're clear it's a product and not a dot. Okay, the magnitude of B like that. Now here's what I'm gonna do. I'm gonna break out a geometry property here, the transitive property. If I tell you that cosine of theta is equal to this equation and cosine of theta is equal to this equation, that must mean those two equations are equal to one another. So A dot B is equal to, or A dot B over magnitude A magnitude B is equal to the magnitude of the green divided by the magnitude of B. And remember, we were trying to calculate how long the green projection would be. Like, what is this length when B is dropped down onto A? Well, easy enough to solve. We could multiply both sides by magnitude B. And there's our formula. So sometimes you'll see this written as this. And it's just because the actual vector projection notation is reserved for the actual components. But you'll see that the length of B onto A is given by the formula A dot B over magnitude of A. And again, it's just a little bit of trigonometry with some dot product work thrown in. Now, one question that was asked earlier in a different video and was, how do you take a vector and make it a different length? The easiest way to do that is to calculate the unit vector and then multiply it by whatever you want the length to be. So I want you to think about this. If I wanted to figure out what the components are of A, which really is this. What are the components? the components of the green. Okay, not just its magnitude, but its components. Well, it's in the same direction as A, but scaled with this value. So here's what I'm going to do. I'm going to find a unit vector for A. Okay, so let's start with that. What do? Well, to find a unit vector, we always find the magnitude, and we take the original vector and divide it by the magnitude. So I'm going to just make a note here. The unit vector for A is vector A divided by magnitude A. All right, that's how we find a unit vector. So if I want to take my vector here, vector A, and make it the length of the green, I simply will multiply this scalar times the unit vector. So imagine you do that, you say, okay, I got to find a little room. A dot B over magnitude A multiplied by A over magnitude A. So the formula simplifies to be A dot B over magnitude A squared times vector A. And I'll do an example to show you how that works. And this is the actual components, because we're just multiplying a vector by a scalar, that make up the green. Okay, let's do an example. So the first thing we're going to do is the scalar. So let's write down the components here. The red, the B, components are 3, 3. The blue, the components are 4, 2. So my scalar, remember, this is, if I can draw this, B gets dropped straight down 90 degrees, like this. If I want to say how long is this projection from beginning to where that line hits, this is what I'm now just calculating the length. I will do A dot B. 3 times 4 is 12, plus 6 times 2. So 12 plus 18, or 12 plus 6 is 18, over the magnitude of A. So 4 squared plus 2 squared. So 16 plus 4. It is the square root of 20. So this is the length, the magnitude of that vector, that length of that yellow thing I just drew. Now the next part is, okay, we'll come up with the actual components of the yellow. This is the projection. So we take our number, or our dot product, which we'd already calculated to be 18. We put it over the magnitude squared, so of course square root of 20 squared is just 20, and we multiply that by the vector A, which was 4, 2. So we have a scalar multiplied by 4, 2. Now, maybe I'll just say this is 9/10, and I'm actually going to do some decimals here. 9/10 times 4 is 3.6. 9/10 times 2 is 1.8. Okay, and I want you to look at this vector, this yellow vector. See how it went over 3.6 and up 1.8. This is the vector that's made when B is projected onto A. Now, this has uses. It's a lot of physics uses dealing with force and how forces act, because forces, we typically think about them acting at 90-degree angles or orthogonally. So this is where the use is in calculating these projections.